Today we're going to look at a really nice binomial coefficient identity known as the hockey stick identity. And it has the name the hockey stick identity because if you look at the numbers involved in this identity, in this case these binomial coefficients, in Pascal's triangle, remember Pascal's triangle is built out of binomial coefficients, well, the shape that those numbers make is a hockey stick. So this left-hand side is what I'll call just the long straight part of the hockey stick. And then this right-hand side is the portion of the hockey stick that you hit the puck with. I apologize if there's a name for that. I don't actually know anything about hockey. Okay, so let's look at this identity. And then we're going to actually prove it 3 different ways. And I think these are 3 very different ways. They don't really look similar to each other at all. Okay, so it's going to be the sum as j goes from k to n of the binomial coefficient j choose k. And that's equal to n plus 1 choose k plus 1. Okay, so let's just jump right into it. And we'll do that by just starting with this left-hand side. So I'm going to go over here and write this left-hand side down. So the sum as j goes from k to n of j choose k. But I'm not going to stop there. I'm going to multiply this by x to the k and then sum that whole thing from k equals 0 to n. So I've got this double sum occurring here. And I kind of want to think about this number that I'm putting in these peach parentheses as my inside sum, and in fact that's the coefficient of x to the k. Now what I'll do is I'll change the order of summation. So that means I want to make my k summation on the inside and my j summation on the outside. So that means I'm going to have the sum as j goes from 0 to n. Because if here j is going from k to n, but k could start at 0, well, in the end, if we change the order of summation, all the possible values of j tend from 0 to n. And then let's see, now we'll have k going from 0 to j. And that's because notice that j starts at k. That means that k has to end at j. I think that's pretty clear, hopefully. And then, well, we're going to have the same argument here. So that's going to be j choose k, and then we'll have x to the k. But now let's put some green parentheses right here and observe that since our x is raised to the kth power, now that's part of the inside sum, whereas over here it was not part of the inside sum. Okay, great. But now we can use the definition of a binomial coefficient as the coefficient in a certain binomial expansion to rewrite this green. So I'm going to take this and I'm going to rewrite it as the sum as j goes from 0 up to n of 1 plus x to the j power. And again, binomial coefficients are defined so that we have this expansion that occurs right here. I could even put some green parentheses right here just to underscore the fact that that's where it's coming from. But now what I'm going to do is I'm going to write out some terms of this just to get some more intuition of what it looks like. And that is 1 plus x plus 1 plus x squared all the way up to 1 plus x to the nth power. So that's what we would get if we were to write this sum out without summation notation. But now I'd like to observe that I've got some sort of standard way of adding all that together. We can actually think about this as a finite geometric series, and there's rules for a summation of a finite geometric series. This is actually going to sum up to 1 plus x to the n plus 1 minus 1 all over, well, it's going to be 1 plus x minus 1, in other words, x. So again, that's just from the summation rule for a finite geometric series. So now what I'll do is go over here and I'll re-expand this 1 plus x to the n plus 1. And that's going to expand as the sum as k goes from 0 to n plus 1 of n plus 1 choose k times x to the k. And then we're going to subtract 1 from that entire thing. So I'm going to put some parentheses around this just to make sure that we know we're subtracting 1 from that entire thing, and then we've got an x in the denominator. But now I'd like to observe we can simplify this a bit. We can take this 1 and observe that 1 is going to be the same thing as n plus 1 choose 0 times x to the 0. So that means we can take this 1 and have it eliminate this 0th term, which means now we're starting at k equals 1. And then we can also take this x and make it change the exponent of the x there to k minus 1. So now we're left with something like that. So our next step, which is in fact going to be our last step, will be to re-index this sum. So I'm going to take every k in this sum and I'm going to replace it with k plus 1. So let's see what that leaves us with. Now we'll have the sum of n plus 1 choose k plus 1 times x to the k. That's what we get from those changes, all the k's replaced with k plus 1. Now, what about the bounds of summation? So let's observe that if k equals 1 and we've exchanged k for k plus 1, well, we have k plus 1 equals 1. But k plus 1 equals 1 exactly when k is equal to 0. But then notice that the upper bound is going to similarly change to n. But now let's look at our starting point and our ending point. And let's observe that what I have here in these peach parentheses on both sides are the coefficient of x to the k in, well, a sum as k goes from 0 to n. So now what we can do is simply extract the coefficient of x to the k from both sides of this big equation, and we have the sum as j goes from k up to n of j choose k equals n plus 1 choose k plus 1, as desired. Okay, so there's our first method of proving this identity. Now let's look at the second. Thanks for sticking around this long into the video. If you're enjoying the video, make sure and give it a thumbs up, and if you're not yet subscribed, think about subscribing. It really helps us out. Okay, so the second method we'll use to prove this identity will be a proof by induction, and we'll induct on n. So I think our base case here would perhaps be the case when n is equal to 0. So let's see, we'll take the n equals 0 as our base case. But notice that's going to make the left-hand part here the sum as j goes from k up to 0 of j choose k equals, what's it going to be? 0 plus 1, which is 1, choose k plus 1. So let's see, we've got 1, choose k plus 1. But let's notice that if k is not equal to 0, then that means that this simplifies just to 0 equals 0, which is, of course, a true equation, right? So if k is not equal to 0, well, this base case holds. And well, we can see that because if k is not equal to 0, let's observe that this left-hand side is an empty sum because it starts further than it ends, but an empty sum is always equal to 0. And then if k is not equal to 0, then we have 1 choose a number bigger than 1. But by the definition of binomial coefficients in terms of subsets, that doesn't make any sense. That would be a subset of a 1-element set with more than one element. So a 2-element subset of a 1-element set. But like I said, that doesn't make any sense. So anyway, if k is not equal to 0, this is true. But now if k is equal to 0, let's observe that over here on the left-hand side, we'll have the sum as j goes from 0 to 0 of j choose 0, or maybe I'll just say, yeah, j choose 0 because it's j choose k, equals 1 choose 1. Now 1 choose 1 is 1. But then this left-hand side of the equation is simply 0 choose 0, which is also equal to 1. So again, we've got a true equation here, which means our base case is satisfied, the n equals 0 case. Now, if you're psyched, you could check it for the n equals 1 and 2 case by hand, and that might give you some more intuition of what's going on here, but we're not going to do that. Okay, so now let's maybe make an induction hypothesis. So let's suppose this is true for the nth case. So that means it's true for some fixed n. We have that equation in blue. Great. And now let's consider the n plus first case. So if we consider the n plus first case, we really have n plus 2 choose k plus 1. Because if we replace n with n plus 1, well, of course, n plus 1 is n plus 2. I think that goes without saying. All right, nice. So now what we're going to do is decompose this using the standard recursion for binomial coefficients, the one that you use to build Pascal's triangle. So this is equal to n plus 1 choose k plus 1 plus n plus 1 choose k. But now we can apply the induction hypothesis to the first term over there on that right-hand side. And that's going to give us this sum as j goes from k up to n of j choose k. And then we have plus n plus 1 choose k. But now let's observe we can just push those two things together by changing the upper bound of summation. So here, this is the same thing as the sum as j goes from k to n plus 1 of j choose k, given the fact that this is simply the n plus first term in this sum down here. But that's all we needed to do to prove this by induction. So we're done in this case now. Okay, so now we've got one more way to prove this nice identity. So before we finish everything off, I'd like to tell you about my second channel, Math Major, where we have full courses in mostly upper division math classes. And in fact, they're ad-free. I have ads turned off on that channel. And that's thanks to my support on Patreon and YouTube channel memberships. If you'd like to help me keep those ad-free, although there's no pressure, maybe think about becoming a patron or joining our channel memberships. Okay. So now let's get back into our third way of proving this identity. And we're going to do this with a combinatorial proof. And that means that we're going to take the, in this case, right-hand side is what we'll start with, and we'll describe it as some certain combinatorial scenario. And then we'll describe it another way via a combinatorial scenario. And well, in fact, what we've just done is counted our methods two different ways. All right, so anyway, we're going to start with n plus 1 choose k plus 1. And I'm going to think about this as the number of ways to choose a k plus 1 person team from a total of n plus 1 people. And then what we're going to simultaneously do as we think about this number of ways to choose the team from a total of n plus 1 people is we're going to put the people that are involved in this scenario, the n plus 1 people, in a line by their height. So that means person 1 is the shortest, person 2 is next, person 3 is next, and so on and so forth. So that means that person n plus 1 is the largest or the tallest. And I know that the proportions here are kind of wacky, but that being said, we're just kind of getting an idea of what's going on here. Okay, so now what I'd like to do is count the number of ways we can build this team another way based off of the tallest person on the team. So let's observe that it's impossible for person 1 to be the tallest. And that's because, well, there's no way we would have a k plus 1 person team if this person is tallest. There aren't enough people to add to the left here. In fact, there's not enough people to add to the left of a 3-person team, assuming that k is large here, because we want a k plus 1 person team, and there's only 2 people shorter than person 3. So we're going to keep that in mind, and that means that the team that we'll start with will be the team where the k plus 1 person, let's maybe put that person right here, is the tallest. Okay, so that will be our first scenario. So we'll have the number of teams where person k plus 1 is tallest. And to that, we're going to add the number of teams where person k plus 2 is tallest. And then, well, we're going to keep up this scenario until we run out of tallest people here. So that would be the number of teams where person n plus 1 is tallest. So there's no one taller than n plus 1, so of course we have to stop there. Okay, but now we can describe each of those possibilities via binomial coefficients. So let's see, we're choosing a k plus 1 person team. So if person k plus 1 is tallest, that means we have k people to choose, and we've only got k people shorter than person k plus 1. So that means we have k choose k possibilities here. Of course, that's only one possibility, but just to keep the structure, we'll say k choose k. And then let's move on to the next case. So the number of teams where person k plus 2 is tallest. So there are k plus 1 people shorter than person k plus 2. We need to choose k of them. So that's clearly going to be what? K plus 1 choose k. And then we'll do that so on and so forth until we get to the very end. So the number of teams where person n plus 1 is tallest. Well, that means there are n people that are shorter than person n plus 1. We need to choose k of them. So we'll have n choose k for the end. And this is just building up one at a time. So the ones that are missing here are like k plus 2 choose k, k plus 3 choose k, so on and so forth. But now we can push all that back together into something with summation notation, and it looks like the sum as j goes from k up to n of j choose k. But again, if we look at the extreme left and right hand side of this equation, we have arrived back at our hockey stick identity. And that's a good place to stop.